Hello everyone. So we're going to move into the section number 2, unit 4. So this section, we planning to discuss about the laws for the fluid or fluid mechanics. That means static fluids and the dynamics of the fluids. So we're going to talk about the laws that valid for the fluid. That means it will valid for the liquid and gases both. So usually we discuss the laws for the liquid in the session, but that will be the same laws valid for the gases too. So now under this session that we are planning to discuss about the pressure principles, including Archimedes principle, Bernoulli principle, and also about the floating objects, sinking objects, submerging objects, why that will happen, and why we will feel like apparent weight is basically less than the weight of the object when you jump into the swimming pool. That's the force of gravity that we feel, why they are different. So these kind of things we're going to discuss in this section. So now if I share my screen, this will be your chapter number 11 and 12 together in the textbook. Okay. So now let's move into the presentation. Okay, so basically I will start with the phases of matter, and then we're going to discuss about the density that you already know it, and then we're going to talk about the pressure in fluids and move into the Pascal, Archimedes, and also Bernoulli and continuity equations. Those are the main part of the this chapter. And phases of matter. So we already know there are a variety of states like solid, liquid, gas, and plasma. So solid and solid we discussed in the earlier chapter, and the liquid and the gas that we're going to discuss in here will be, we call it as the fluid, right? So fluid can be a liquid or the gas. So now we discussed about the solid last time. So what is the solid is? Solid is basically a kind of rigid structure that you can say there is a periodic pattern of arrangement of atoms that has the definite volume and definite shape, right? That's called it as the solid. Now solid can be divided into two parts, crystalline solid and amorphous solid. So crystalline solid is the solid that you have a periodic pattern. The arrangement of atoms is keep repeating the same pattern. We call it as the crystalline solid. Simple example is salt or sodium chloride we use in day-to-day life. And then amorphous solid does not have that orderly arrangement throughout the structure, but they may have boundaries that will destroy the arrangement of the pattern. Those we call it as amorphous solid. Simple example is glass. So now we discuss about the liquid. Liquid does not have the definite shape, but it has the definite volume. And then gas, definitely not a definite shape or the volume. And plasma is ionized gas and is most common that we're going to discuss in the matter of the universe. Okay, so now liquid, again, gas, these two, we call it as the fluid. That's the part that we're going to discuss in this chapter. Okay, and now first thing I need to explain is the density. So you already know the density because we did the first experiment about the density. Density is the one of the property of the material. That means if you take the copper piece, small or larger, it doesn't matter the size of the material. You have a material property that we start in the beginning, that is the density. Density will be mass over volume ratio to the mass and volume we call as the density. Okay, so now density units will be usually measured by using grams per centimeter cube, but SI unit will be kilograms per meter cube. Okay, so now water has the density around 1 gram per centimeter cube at 4 degrees. So that's very specific in the water, because water densities keep changing with the temperature. That is the maximum that you can see here, temperature around 4 degrees, that you have the density 1000 kilograms per meter cube or 1 grams per centimeter cube. That's the density that we call it as the standard density of water, but that is 4 degrees of Celsius. Okay. And next quantity we're going to discuss is specific gravity. Specific gravity is the ratio of density of the material divided by the density of the water at 4 centigrade. That ratio we call it as specific gravity, and it is unitless because it's just the ratio. Okay. And let's move into the pressure. So now everybody know the stress that we are feeling, that will be basically force per unit area will be the definition of the pressure. So pressure is defined as force per unit area, right? So that means it is not exactly same thing as force. As a simple example, if we try to push my finger by using tip point of the pen, so that hurt my finger, that not because of the force that you are applying, because force you applied for a small tiny area, then it will hurt because of the pressure that I have it in that tiny area, right? So that is the definition of the pressure. Now, immediately you will see the units, newtons over meter cube, meter squared, right? Newton over meter squared. So that unit, we call it as the Pascal. Pascal is the scientist name. Okay. So now, in addition to that, that is the SI unit. There are ATM units some people use, especially when you measure the pressure at atmosphere, we use the atmospheric pressure. And there are many other units that we use for the measurement of the pressure, but we can convert those back into SI units. So, but what the actually pressure looks like. So as a simple example, when I sit on this air will apply the pressure on my body, right? So that pressure will always apply everywhere in my body surface that has the perpendicular to my surface will be the pressure application everywhere in the body. Similar to that, if you drop something into the water, there is a pressure applying from every direction perpendicular to the surface. And even when the water inside the beaker, there is a pressure applied because of the water to the container. That component will be always a perpendicular component. That means there is no parallel component of the pressure on the force, especially because force per unit area is the pressure, right? So now this is another example that you can see. This lady can stay on these needles without hurting her body, because you spread out your whole weight to many needles. Then it is okay, or it is safe to read the book on needles. Okay. Now pressure at any point you will be able to calculate by using density of the fluid times the G times the H. What that means is, if you have the pressure at this point, we'll say this point pressure is 0. It's not 0, but that is my reference point that I'm going to see pressure is 0. So now if I need to calculate the pressure at this point, that will be the pressure P1 equal rho G, and the height from here to here is H. So rho is in this case fluid density. Whatever fluid you are using times G times H will be the definition of the pressure. That how you calculate the pressure in different locations, right? So it can be easily derived by using the definition of pressure and by using the definition of the density. Okay, so now as I mentioned earlier, so pressure can act on the air or any liquid or fluids, right? So now if you measure the pressure that one point, we'll say I have here, I have the pressure 0 point or P0, whatever pressure at that point. If it is atmospheric pressure, that will be 1 atm, 1 atm. And now if I need to find the pressure at this point, we'll say P1. If this one is vertical height H, and if this density of the fluid is, we'll say rho 1. Then this P1, I will be able to calculate. I'm going to write in this way. P1 equal P0 plus rho 1 G and H. What is the G is? G is the 9.80 value, right? So now if I need to calculate the pressure in some height, not the depth, pressure number 2. So now pressure number 2 will say this is still H, and I have the fluid here, fluid number 2, a different fluid. So now pressure at this point will be equal to P naught pressure, that means this pressure, and you need to subtract rho 2 times GH. So what that means is when you go into the height, your pressure is decreasing, but when you go to the down depth, pressure is increasing. That's why the low air pressure, that the particle, when they have low pressure, they will go to the lower dense particle will go to the lower pressure, right? So, and also, you know, that helium balloons going upward because they will go to the low pressure region. Okay. And so now let's think about this example that I have a can that I have static flow in the static fluid, right? No flow in, so fluid is there. But if I write pressure on this each point, we'll say this is my A point, B point, C point, D point, and E point. So now I have holes that can pump the water. So now if you watch the path taken from this each water from those points will be land in different places. That means range is different. What that means, this range is RA, and this range from here to here will be RD, RE, sorry, RA, and this range I have for the F, for DE. So your range from the E point pumping water is very, very small than the range from the A. So now the bottom hole pump the water to the longer range. Why it is happening? Because now we discuss about the pressure change with the depth. That means definitely pressure at A point is greater than pressure at B point, greater than pressure at C point, greater than pressure at D point, greater than pressure at D point. So because of that, this has high pressure. Because of that, it will go the parabolic path with the longer range. Okay, so now pressure at same height will be the same. So what I mean is pressure at this point, this point, this point, this point will be the same. So now if I use the same liquid for this each shape of the tube, they also going to stay in the same level, right? But if I have a different liquid, still I'm going to say pressure at A, B, and C are the same, because that's the principle of pressure at same height. I should have same pressure. That's the principle. So now, if I have different liquid, different density liquid, what will happen is this level may change, because if you have a high density material, then definitely your liquid level will be go somewhere. If you have low density material, your liquid level somewhere here. So according to the liquid that you use, according to the density that you have in the liquid, your height will be different, but still your pressure at this point that you calculate rho g times different height will be the same, because when you have high density, H should be lower. Okay, that's how it will change, because G is a constant. Okay, so now let's move into the Pascal principle. What the Pascal principle is? Pascal principle is basically definition of the pressure. Pressure equal force per unit area. That's the Pascal principle is. Now, we can use the Pascal principle for this hydraulic brake system or the hydraulic lift, that when you bring your vehicle to the maintenance, if you need to lift it up, this is the pistons system that they use for lifting the vehicle. So because it can lift tons of object by using a hydraulic lift, right? So let's see what is happening in here. I have a piston in here. I'm going to apply the force F1 to area A1. Then when I apply the pressure on that side, then the other side will create a force F2 upward direction, but acting on the larger cross-section area. So now pressure 1 and pressure 2 are equal. You can take any 2 points on this beakers, same height, same pressure. So now force per unit area are equal. Then you will be able to find the force that you can lift the object on the right piston, right system, that will be a greater value than the F1. Why it is greater? Because your cross-sectional area is greater. Because of that, it will have greater force, called as the hydraulic lift. Okay. And there are many other applications, barometers, pressure gauge meters, air pressure meters, those all are application of the pressure. So here I have simple example, open tube manometer. So this one, you can measure the pressure at this point, this pressure that everywhere in this point will be almost the same pressure, right? So pressure at this point is atmospheric pressure. Now, if I want to find the pressure at this point, I know how to find it. This pressure times the rho, G, and H will give me the pressure that I want to calculate. So now H will be basically this height. That means you need to take the density of this fluid to the calculation. Then you will be able to find the pressure that you need to find it out. Okay. So now in addition to that, when you go to the doctor office, you are measuring pressure by using pressure meters, and air pressures, we are measuring gauge pressures, you are measuring, but make sure that you know how to do the unit conversion, because they are not using Pascal sometimes, especially in doctor office, we use the mercury millimeter units. So you should know how to convert that into the Pascal. Okay, those units should be converted always into the SI unit when you compare the values. Okay, so but I would like to move into the barometer. Barometer is the instrument that we can measure the atmospheric pressure by keeping it in atmosphere, right? So now, if I use we'll say if I use the container, then I have mercury, Hg or mercury. So, and then I have a tube, right, beaker. So then I'm going to fill up the tube with the mercury and tip it over inside the mercury container. So now after I do it, you're going to see that this mercury level going to stay at 76 centimeter, independent of size of the beaker, independent of how much liquid that I'm going to put it in there, and independent of the size or tall height of the beaker. So none of these matters. It will always come to the 76 centimeter line. Why it is happening? So now you will be able to understand it, because you see in the pressure at this point is atmospheric pressure. I told you pressure will be the same for that height everywhere. That means pressure at this point will be equal to the atmospheric pressure. That means pressure, the point that I am working is actually equal to 180. Right. So now another way, this pressure I will be able to write by using the vacuum pressure here is 0, then rho times G times H will be equal to the rho of mercury, G times the height will be equal to the 180. Then make them equal. Then you will be able to find the H. After you plug that into your calculator, you're going to get the H equals 76 centimeters. That's the reason it will going to stay in 76 centimeters. So now think about that. If I use the water, can I use the water for barometer? Can I use the alcohol for the barometer? So that's not, that will work. But only issue is the density of the water is much smaller than the density of the mercury. Because of that, you need the taller tubes, like 10 meters will be the length that you will get for the water. Alcohol may be greater than that, because it is inconvenient. It's not easy to use that kind of setup to measure the, because setup wise, it's a big size, the tall, that will not be easy to use like mercury. That's why we use the mercury high dense liquid for this purpose. Okay. And now we're going to move into the Archimedes principle. Before that, I would like to talk a little bit about buoyant force. So buoyant force will happen everywhere. In myself, when I sit in on this air will create an upward force on me. That is the buoyant force. When I jump into the swimming pool, I will come to the level of the water because there is a buoyant force. So now submarines will have the can stay inside the water, and the ship can float on the sea level. Why these things happening? Because of the buoyant force. That force is always acting upward direction on the object. How do we calculate that amount? So that we'll be able to calculate by using this formula. We can easily derive as I have it in here, but important thing is understand the concept. So the buoyant force of the object will be able to calculate by using fluid mass, that will be displaced fluid mass times the G. What that means? So what that means is, if I have a beaker, we'll say I'm going to pull this with some liquid, right? And then I have another beaker here. I'm going to collect the water when I drop something. So we'll say I'm going to drop an object in here. Now, since it is full of water, when I drop it, there is no space for displaced water. Then part of the water will be collect into your beaker and basket, and then you're going to measure the mass of that. Take the mass of that part. That will be the mass of fluid. Okay, then times the G value will give you the buoyant force. Okay, so now that's very important concept. Then we know how to calculate it, but how it related into the real life example. Simple example is, if you put something in the water, that object sink, float, or submerge is depend on your force of gravity and the buoyant force. If buoyant force is greater, definitely come to the top. If force of gravity is greater, definitely go in and sink, and submerge will be basically they may come to the some equilibrium forces. But the everything that I discuss will work for the air too. So you see that in here, buoyant force is greater than the force of gravity of the helium balloon. Because of that, it will go in upward direction. Okay, so now as I mentioned that if you put something inside the water, so when they are equal on the buoyant force and the force of gravity, they will come to the float and stay exactly at half and half. You see half and half size, right? They are come to the water level because they are equal. But in simple example, we'll say this level of sinking, and also that means inside the water and outside the water of the object is depend on the densities. So now this will be able to calculate by using this equation. This is also very simply derived, but we can calculate the density ratios by using how much that object inside the water, how much that object outside the water. By comparing that, you will be able to calculate the density. So this is density of the object. This is density of the fluid. And this V displaced is the volume of the object that are inside the water. That means if you take the volume of this part, that is what the V displaced means. Or else the mass that you're going to count, you have a volume in there, that volume. Okay, so now V naught is the total volume of the object. That means your total volume is the object will be, basically you take all volume in here, that is the total volume. Okay, so that formula will be easy to use. Okay, so go back to state the Archimedes principle. Archimedes principle is saying that if you put the object inside the water, that object can be partially or completely immersed on the liquid. The magnitude of buoyant force will be equal to the weight of the fluid that displaces because of that object. That is the Archimedes principle. And in addition to that, definitely you have an idea that when you have something, like example, if I have an object that I measure the mass, we'll say I have measured the mass of this object by using a spring balance, is saying the mass of the weight of the object is 10 newtons, something like that. You measure it 10 newtons. But if I add the water to this one, you put the object inside the water, then this reading will going to turn down a little bit. I don't know how much, it depends on the buoyant force, but we'll say it reduced to some number that we call it as the apparent weight. It's not the real weight, it is the apparent weight. Apparent weight will be always weight minus the buoyant force. Okay. Okay, so liquid, as I mentioned, sink, neither sink or float, is depend on buoyant force and the force of gravity. Buoyant force is greater than force of gravity, lifting up, otherwise it's going down, right? So that will be basically idea about this float and sink. Another way, floating and sinking, you can describe by using the density of the material. If object is more denser than the fluid, it definitely sink. If less than the fluid, it will float. Otherwise, neither sink or neither float will work. Okay. So we're going to move into the fluids in motion. Everything that we discussed so far is static. Now we're going to move into the dynamic. Although we are moving into the dynamic part, actually we are doing this simple flow that has a smooth flow. We call it as laminar or streamline flow. That means we are not going to include the turbulence that as I have it in here. Turbulence flow, these rules not work. So we're going to do some simple conceptual understanding for the laminar flow. Under that, we're going to discuss about the fluid in motion, especially equation of continuity and flow rate and Bernoulli principle. Okay. Okay, so give me a second. Okay, here. So now first thing is the flow rate. Flow rate means basically mass per unit time. How much mass you can transfer per unit time, we call it as the flow rate. So now if I transfer the mass per unit time, some amount in here, that is flow rate, that we use the letter Q for that. Flow rate, letter Q. Mass per unit time, right? So now that will be exactly same on the other side also. Though your tube cross-sectional area change, Q value in left side and right value is the same. That means flow rate is the same inside the tube. That is called it as the flow rate. Okay, Q1 equal Q2. So now what is the continuity equation saying that if you have same liquid, same fluid inside the tube, depend on the cross-sectional area, your velocity of the fluid is different. So simple example you can watch in here. So I have the velocity V2 in the cross-sectional area A2 and velocity vector is very big for the cross-sectional area A1, which is less than the A2. That means when you have A1 V1 equal A2 V2 formula is the continuity equation that I can say basically when the cross section is smaller, that means your velocity of the flow or the liquid is greater. So that is called it as the equation of continuity. So now if the fluid is the same, otherwise you need to add the density of the fluid if they are different fluids. Okay, that means A times V is constant on the tube. Okay, so that is the continuity equation. So now we're going to move into the Bernoulli equation. So now Bernoulli equation, theoretically, I'm not going to derive it, but conceptually, but the Bernoulli explaining is relation between velocity and the pressure. Velocity and the pressure relation is explained by the Bernoulli principle. What that means is now we know when the cross-sectional area is smaller, velocity is greater. According to the tube size, you can decide that. That is continuity equation. But after you find the velocity connection, then you can say, okay, when the velocity is greater, you have low pressure. When the velocity is smaller, you have high pressure. So that is call it as the Bernoulli equation. That means the thinner cross-section areas you have basically low pressure because velocity is higher. So getting narrower of the tube. Okay, that is what the Bernoulli explained, right? So now this is, you can see it is horizontal tube, but you can have a different height tube. We'll say I have exactly same velocity in here and same velocity in here, but according to the Pascal principle, we definitely know that we have high pressure in here because you get in depth than the your point on the right side. So height is different because of that. Pressure at left side is greater than the pressure at right side, as you can see, high and low in here. That is again explained by not only Bernoulli principle, it is explained by Pascal principle, but Bernoulli add this everything together into the formula by combining velocity and pressure together. Okay, so that's what the Bernoulli says. So Bernoulli principle will be easily derived, but it says this is a constant. So pressure plus half times rho times velocity square, this is actually energy. And then you have the energy density, and this will be rho g and the vertical height. So it includes the Pascal principle in one way, that is this part. And another way, it will include the pressure and velocity relation. Okay, that's what the Bernoulli say. So when the velocity is greater, pressure is lower, and when the height is greater, you have low pressure. So this is what the Bernoulli principle explained to you. So very easy to think by using this equation. Let me erase it and draw it. When velocity is increased, since it is a constant, your pressure is decreased. That is one phenomena that explained in the Bernoulli, and the other phenomena that explained in the Bernoulli, when you have vertical height is greater, that means you have low pressure. That's the relation of the Bernoulli equation. Okay, so now by watching this diagram, you're going to do the exactly same problem in your recitation session, but I have the areas labeled, the portion of the tubes labeled as 1, 2, 3, and 4, right? So I am asking you to explain the flow rate. So now if it is the same fluid, the flow rate, whatever I push it in left side will go to the right side. That means mass per unit time will be the same. Flow rate will be the same for everywhere, right? So now asking about the velocity, how the velocity change, you need to go back and think about the flow rate. That means cross-sectional area times velocity is a constant. Think about that formula. What that means is when the cross-section greater, velocity is lower, right? So now where the cross-section greater? So here is the lowest velocity, right? Here is the greatest velocity. Now velocity of 1 is greater than velocity of 2, greater than velocity of 3, greater than velocity of 4. So now asking about the pressure. To study the pressure, you need to go to the Bernoulli principle. But the Bernoulli is saying that when velocity is increasing, pressure will decrease, right? So in addition to that, when height is increasing, pressure decrease. So that's the two things that explain in Bernoulli. So now let's take V1 and V2 are the V1 is greater than V2. That means definitely the velocity that I have it on the 1 is greater, because of that pressure 1 will be lower than the pressure 2. Okay, so now let's go into the 3. So now 3, definitely I know pressure is, so your size is the same, right? But your velocity, I'm sorry, I think I did the mistake, because 2 and 3 are actually the same cross-sectional area. That means these two velocities are the same. These two are the same, right? So now velocities are the same, but we know that the pressure at 3 is greater than the pressure at 2, because of the 2 is higher than the 3, right? So now pressure at 3 is actually greater than the pressure at 2 because of the depth, right? And then 3 and 4, velocity is greater in 3 than the 4, then because of the pressure will be less in P3. Okay, that's how Pascal principle, Bernoulli principle, flow rate principle, continuity equation, everything together apply into this simple conceptual question. Okay, so now last thing I'm going to discuss is Bernoulli principle. This is talking for the laminar flow. It's saying that it is saying basically the pressure difference. If you have the tube, horizontal tube, that you measure the pressure at one end and the other end, these two different pressures will give you the flow rate. flow rate is defined according to this pressure is called it as the Poiseuille principle. So now what is that mean? So you take the pressure difference and divide by the R will give you the flow rate. If we have different pressure in the same tube on the horizontal line. So now what is the R is? R is relation actually to the friction of the flow. That means the viscosity of the flow will create this pressure difference, because we told that we have the same pressure in the same horizontal line if it is static, but when the laminar flow happen in these two may have a different pressure, although they are sitting in the same height, because of the viscosity of the liquid. So now that include into here, that is what the Poiseuille principle do, and then your equation will be turned into this one. Okay, so I think that's enough for the fluid part.